Alright, so this video is going to be basically just some basics of magnetism. Turns out that in order to create electricity, we already know about the electricity part of it, current and voltage and resistance and all that stuff, but in order to create electricity easily, it really has to do something with magnetism. So if we, excuse me, if we take a magnet, and I'm sure you guys know that magnets end up having two sides to them. They have a north end and they have a south end. Okay, a north end and a south end. And I'm sure you're also aware from your own dealings with magnetism that if you were to put another north end to this north end up here, then they would repel, right? Because the north doesn't want to be next to a north. If you were to put a north end down here, however, then we would know that they would attract. This is very similar to what we've already discussed in terms of just charges, how two like charges will repel but two unlike charges will attract. Well, it really turns out that magnetism and electricity or electrostatics are very, very closely related. So it's kind of a no wonder why they end up exhibiting themselves the same way. But let's go back to our single magnet. Now we know a single magnet with the two ends will tend to do funny things when you kind of let them. So this goes back all the way to early Greeks and after that when they figured out that there are certain materials that have this magnetic property that it attracts other metals. And someone along the line figured out that if you were to set the magnet in something that can freely rotate. So people routinely would do it like set it on a leaf or something like that and put it in water. Then it turns out that your magnet would always orient itself so that one side of the magnet pointed towards the north, the geographic north, and the other side of the magnet would always point to the south. And we're talking about geographic location. So this is the reason why we call these north and south. It's specifically saying this is the south-seeking side of the magnet, and this side is the north-seeking side of the magnet. But let's go back to what we talked about, how a north and a north will repel, and a north and a south will attract. So if that's the case, if we have labeled this side of the magnet as being a north side of the magnet, then what does that mean about the Earth's magnetic field? Okay, there's the Earth's magnetic field, and if we have a little magnet here that has north up here and south down here, then what does that mean about the actual magnetic properties of the planet? Well, a north is attracted to a south, and a south is attracted to a north. So the Earth's magnetic properties are actually backwards from what we have um, set in our compass. The compass points north, but we actually call that the north side of the magnet. So this is kind of weird how in the north, at the top of the world, the magnetic field or the magnetic pole is a south pole. And then down here at the bottom of the world, at the south geographic pole, we actually have a north magnetic pole. And this really comes down to just naming, right? We named this before we really figured out exactly what it was doing. It's a north-seeking side of the magnet. It goes to the north geographic position, but a north and a south are the things that attract. So therefore, that magnetic pole up there has to be called the south pole. So hopefully that's not incredibly confusing. Uh, but we can also use compasses for another thing. If we take our magnet again, and again we have our north side and we have our south side. Now in black I'm going to draw directionalities of a magnet. If you were to put a magnet near a north pole, then the compass were to put, excuse me, if you were to put a compass near the north pole of this magnet, then it's going to point in this direction. Pointing mean it's going to have your little north right here and a little south right here. So we're saying that the north side of it is a pointer. If we put it down here by the south pole, then it's going to point like that. Okay, again, a little north right here, a little south right here. If we put it over here on the sides, what you would actually find is that it would point this direction. Got north here, south here. And again, on the other side, it would be the same thing. North here, south here. Now, if you were to put it at the corners, what you'd end up finding is that you would have something that looked like this. North there, south there. And keeping on with the kind of pattern, there we go. Okay. If we were to actually start connecting the dots, I'm going to do that in green. Start connecting the arrows, and I'm going to do it a little bit more fluid, like what we would usually draw it. We would see that we have something going on that looks like that. And there's a directionality to it where it's coming from north and going to south. Same thing happens over here. We have a north going to a south. So what have I just drawn in green? Well, in green is what we call the magnetic field. It's the area around a magnet that has the ability to affect other magnets. Okay, it's similar to what the electric field is, where it's an area around a charge that has the ability to affect another charge. But now we're talking about magnets here. So they are related to each other, but they're not the same field. We have the electric field, we have the magnetic field. Magnetic field does have a way to quantify it, which means you can put a number here. Let's say right here, the magnetic field was 8. Well, what would it be? The units for magnetic field are Tesla, named after Nikola Tesla, that we'll talk about later. So if we had 8 here, then it could be 8 Tesla. And that would actually be a really strong magnetic field, but it's possible. Now we have something else to owe to another physicist named Michael Faraday. That he was a physics professor, but he also worked in electricity and magnetism. And he was, as the story goes, in class one day, and he realized that when he had a wire of current that he had hooked up to a battery source, and he was turning it on and off. He had a switch here, I guess, and he was turning it on and off. And he had something like a compass nearby. There's your compass, north, south. That every time he turned on the current, the compass needle would jump. It would jump to another place. So every time he turned on the current, the compass needle would jump, which means that if the compass needle is jumping, if it's starting to reflect something else rather than just true north, then we have something else going on in terms of magnetism. Every time the current gets turned on, then it has to be creating some type of magnetic field in order to affect the compass. And that's exactly what Michael Faraday ended up showing. He showed a lot more, but one of his first things was is that a current carrying wire, a wire that has current running through it, electric charges running through it, actually creates a magnetic field around it. And that magnetic field is, it's actually kind of weird. It happens perpendicular to the actual wire itself. So as the current is going this way, your magnetic field is actually circling around the wire. And it's circling in a particular direction if you were to put a compass on it. Okay, so if it's going that way, it's actually circling clockwise, I guess, if you were to take this perspective drawing. So every point has a circle of magnetic field going around it. Now, it's hard to draw it perspectively, so what we end up doing is we say, okay, well, if the current is going into the screen, which we usually symbolize as, if it's coming out of the screen, we usually symbolize it as a dot. So this is I coming out of the screen. What direction would the magnetic field be? Well, we know it's going to be a circle. And that circle can either go one of two ways. It can either go clockwise or it can go counterclockwise. Well, in this particular one, it actually goes counterclockwise. Okay. And what if we said that the current was coming out of the, into the screen? Then we usually symbolize that as an X. It's going in, so that's current going in. Again, we have a magnetic field that's circling around that wire. Okay, but in this case, it is going clockwise. Okay, and how can you remember that? Well, we have a handy dandy little. That's not what I wanted. There we go. We have a handy dandy little trick. It's called the right hand rule trick. So if you put your thumb in the direction of the current, like what it's showing right here, your thumb in the direction of the current, then your fingers curl around the wire in the direction of the magnetic field. It only works with the right hand. If you use the left hand, you get the exact opposite answer. So this is the right hand rule, and that's how you can figure out the direction of the magnetic field around a current carrying wire. All right, so we'll pick up with this again in the next video.